When we have to integrate rational functions, it's enough to consider proper rational functions. So let's start with some examples. If I'm going to have a proper rational function, and if the denominator is a linear polynomial, degree 1 polynomial, that means the numerator would have to be something constant, degree 0 polynomial. So let's take it to be -7. Now, something like this can always be integrated by letting the denominator be equal to u. So if u is 3x minus 1, then du is 3 dx. And whatever number you have, you can always pull that outside the integral and write that as -7 and integral dx over 3x minus 1, which you can rewrite as -7. Now dx is, du is 3 dx, so dx is 1/3 du over u. And this happens to be -7/3 integral of du over u, which is -7/3 ln absolute u plus c, and that happens to be -7/3 ln u was 3x minus 1, so absolute of 3x minus 1 plus c. So to summarize, if you have a linear polynomial in the denominator, your numerator will always be constant, that can be pulled out, and a u substitution will always work. Now, when we go on to more higher degree polynomials in the denominator, say you have a quadratic. So let me say I have a quadratic polynomial, then the numerator could be either a constant or a linear polynomial. So something like x squared plus 6x plus 8. If you have this, then notice this quadratic could be factored, and that should be our first step. 2x minus 1 divided by x plus, that factors as x plus 2, x plus 4. And to integrate this, we'll have to split this into partial fractions, which we will discuss in a separate video. Now, sometimes you won't be able to factor. In that case, so let's look at one example like that. So let's keep the numerator same, and now the denominator, I want to pick something which cannot be factored. So I can take x squared plus 4. Then this cannot be factored. Now when you cannot factor, then you will have to use some trigonometric inverse trig functions, and tan inverse derivative is 1 over x squared plus 1, and we will have to manipulate that little bit and go about doing it. If your quadratic cannot be factored, that's what we'll do. Now what would you do if you had a cubic polynomial in the denominator? Now your cubic polynomial, there is a theorem in algebra that says your cubic polynomial can always be factored as either, so let me write down something like this, over, now the numerator could be either a constant or linear or a quadratic polynomial. So let's just keep it simple, say this is. Then here is the thing, your cubic polynomial can always be factored. It will always have a linear factor at least, and then so a linear and a quadratic. So let me just write this down. This one actually factors as x squared, x minus 1 times x squared minus 5x plus 6, and sometimes this quadratic could be further factored or it need not be factored. In that case, So in any case, you can always split this into partial fractions. And one denominator would have x minus 1 and the other denominator would have x squared minus 5x plus 6. So that's the idea. If your denominator is a linear polynomial, U substitution will work. But if the denominator has higher degree, then the most we'll have to worry about is degree 2 polynomial, because every higher degree polynomial could be broken down or could be factored into something that's linear and quadratic in the case of cubic. If you have a fourth degree polynomial, it may be quadratic and quadratic, but we don't have to worry about anything beyond quadratics.